So, hello, I'm Luis Henrique. That's my qualification. That's the presentation of my qualification work. My main supervisor is Professor Lucas, and my work's titled Automated Verification and Refutation of Quantized Neural Networks. Here is the outline of my presentation. So first I will make an introduction, then the preliminaries, then I will talk about the methodology and then code generation, interval analysis, verification of QNNs. Then I will talk about experimental evaluation that is split in ablation study and to comparison. And then by the end I will make a conclusion. So the background of our research is safety critical systems and AI. On the left, we can see an AI acting along a radiologist. So it's marking regions to examine. So the red areas are marked by NN, and the blue areas are marked by the radiologist. On the right, we can see a mass detection localization in mammograms. So the red contours are ground truth, and cyan contours are false positive. We can see that some of them are quite accurate. So another example of a safety critical system using AI is the self-driving car. So this NVIDIA can park, this NVIDIA car can drive on the street. And it also uses a camera that performs object detection and classification. So that's certainly a safe critical system. Adversarial examples are not simple misclassifications, but particular cases that expose vulnerabilities in AI system. Here we can see a 80-mile speed limit becoming a 30-mile speed limit with only a few cyan pixels, a few cyan noised pixels added. So it's still 80 miles speed limit for a human easily. And unfortunately, some of these adversarial examples can occur in the real world. For example, the self-driving Uber car killed a pedestrian in Arizona. So she was riding a bike, and unfortunately, the self-driving car didn't recognize her as a human, as a pedestrian. So unfortunately, there was this accident, and the woman died. Our overall objectives are showing how unsafe an ANN or QNN can be, and how safety properties behave in QNN. Our specific objective comes from training ANNs with consolidated algorithms, obtain ANNs models and QNNs models. Then we need to model a safety property, explore the best techniques for ANN, QNN verification in SPMC, and comparison our results with some state-of-the-art tools. So here on the preliminaries, we begin with model checking. So the basic idea of model checking is check the negation of a given property up to a given depth. So here we can see a transition system unrolled queue times. So in software, we have this queue can be enrolling loops or recursion. So the base idea is translating to a verification condition C, such that C is satisfiable if phi has counterexample of max depth K. So basically, it will check for each transition the negation of the property C. It's also important to mention that BMC has been applied successfully to verify hardware and software. Another basics here is that artificial neural networks. So ANNs are versatile systems capable of generalizing and responding to unexpected inputs patterns. ANNs are based in simple mathematical operations, basically sum and multiplications compose the neural computations, and learning algorithms. Quantized neural network are also a representation of ANNs. So in this example, on the left, we can see a quite simple ANN with two nodes. And these two nodes use ReLU as activation function. So the output is adding these two neural outputs. So here we expand as a ReLU of the weights multiplied by the inputs. So if we suppose this input vector, we can see that on the real world, this output would be like this. If we compute that on the calculator, we will check this output. But if we are talking about a quantized neural network, for example, we represent floating numbers as the fractional part using only 6 fractional bits, then we would have a quite different output. So regarding this change, we will talk a little bit better further. So here we illustrate how a safety property can be checked. So the safety property basically is born with a base image, a distance metric, and based on these two elements, we will have an interval. So this interval we can consider here as this restriction. So for any possible image that is near to this base image with respect to a metric, then we say that this image is part of the interval. So the safety property will be true, will hold if all the images inside this interval keeps the same output. So for example, this is U, and let's suppose that we have that we already define a metric and we have a range, an interval. So if any image of this interval is classified as U, so the property holds. Our methodology here is illustrated as these 8 steps. So we part from the ANN with weights and bias descriptions. So we already have that. We transform this ANN mathematical model into a single thread C code. Then on the step 2, we represent this code in the fixed point representation. So we will perform a kind of scaling and checking if the ANN is representable on the questioned word length. So on the next step, we cast the activation functions in lookup tables, mainly the non-piecewise linear activation functions. Then we go to the safety property, where we define the property and we insert the assumes into the code. And we also add the property as insert statements on the code. The next step, we compute intervals for the benchmark in question. So we use another tool that we will also talk about this later. By the end, we perform the model checking. We use SMC to check for if the safety property holds or not. So if it fails, then we provide the adversarial example, the counter example, and we need to check if this counter example is an adversarial example. So if it is, then it's we suggest to retrain the neural network using the adversarial example. So if it's successful, then we say that the ANN is safe to use with respect the property. So here, the first step, we will expand it and that black box and talk deeply about it. So we export this C code from the ANN mathematical model. We also perform the expressions balancing. So the basic operations of ANNs are sums and multiplications. So we don't do that in the linear layout, as we can see on the left, that we have only one accumulator that will add all the weights and inputs multiplication. But instead of that, we do the balanced layout. So this code will contain this layout that we perform the adds using many accumulators and not only one. So it will help on the verification process, this layout. On the next step, we have the representation. So basically, we cast the floating part of the ANNs into the fixed point representation. So first, as we specified the word length, we need to split between the integer and the fractional part. So for doing that, we need to check if the worst case are representable using this word resolution. We do that in order to avoid overflow, because if overflow occurs, then we couldn't check correctly the properties. On the next step, we have we cast the activation functions into lookup tables. Here we can see the sigmoid example. So on the left, we can see basically 4 curves. So with different discretization steps. So the yellow is quite over approximated, but here on the right we can see that the red and the blue one are quite has a high accuracy. After the activation function, we specify the safety property into the code. So here we have this example, any general ANN. We have a center that is the desired image. And after we specify the distance, we will have the upper and the lower. So each pixel will have a maximum and a minimum value. So on the input vector, we specified as a sums the maximum and the minimum. So the verification machine will only check these the values inside the range, and then we add the assert statement to keep the same label as the desired one. So that's how we specify the safety property on the code. After we perform the invariant generation, because after we have the intervals determined on the code, we export it to pharmacy. In pharmacy, we compute all the possible maximum and minimum values of each neuron. So we import these intervals into the code as a sum statements for each neuron. We do that in order to reduce state space exploration, since each neuron will have a range, so it helps a lot in the verification process. Then we have the model checking itself. So the source code is provided as an input to ESMC. ESMC will check for failures. So if verification condition is satisfied, a counterexample is provided. If any adversarial examples exist, a training improvement must be done. If no counterexample is provided, then the ANN, we can say that the ANN is robust with respect to the safety property. Now we can start talking about our results. So our benchmark lays on these two neural networks. The first one is the iris. So we have a data set with 150 samples. So 50 samples from each piece of iris is sampled. It was trained on TensorFlow and Keras. Its architecture is 473. It uses hyperbolic tangent and softmax. Then we have a vocalic benchmark. Its data set is composed by 200 samples, and 100 samples are noise and base vocalic image. We trained it using backpropagation cross-validation, and its architecture is 25, 10, 4, and 5. And the activation function used here is sigmoid. And we also have AXAC-Zoo, that is a deep neural network. We didn't train it itself, but we imported it from Redplex. They provided the weights and bias descriptions of the 45 neural networks, AXAC-Zoo neural networks that they trained. So they are all fully connected ReLU neurons, and the architecture is composed by these 6 hidden layers of 300 neurons each one. Now, the first step of our experimental evaluation is the ablation study, where we will compare each parameter that improves our performance, and then we will do the comparison, show the results, and make some analysis. So in the solver comparison, we could see that Bull Lecter overcomes Bituzla, but just a little bit. Any ISIS was have a significant performance, a better performance than Bull Lecter. So EISIS was the solver that we used to perform our to run our benchmarks. Regarding the parameters, we combined each of these parameters to check the best performance, and that these are the best ones. So first malloc success, non-div by zero, no pointer check, EISIS, no bounds check, interval analysis, and fixed the BV. Fixed BV. About interval analysis comparison, we tried ESMC native interval analysis, so it was a little bit better than non-interval, but from a C overcame all of them because its performance was much better. On activation function discretization, we can see that the larger steps have the best performance, and it is due since the steps are larger, the state space becomes smaller because there are less values to check. So resolution 3 is the most accurate one, but the performance falls. About the balanced and sequential layout comparison, we can see that there is not any significant improvement when use balanced layout, and also about the outputs, we have one timeout when using balanced. only one, but it occurs. So balanced or sequential won't change, won't interfere on the performance. This outcome comparison across the lookup tables resolution. Here we can check that for iris, resolution 1 is enough, so it keeps the result of resolution 2. In between resolution 2 and 3, we can see that 3 has some timeouts, so resolution 2 or 1 would would fit better. In vocalic, we can see that resolution 1 performs some different, have some different outcomes when compared to resolution 2. And resolution 2 and 3 also differ in some outcomes. Here we can see the iris verification outcomes across quantization levels. So when we have this lower number of bits, we don't have a pattern. So sometimes it's successful, and then it fails, then it becomes successful again. But as far as we increase this number of bits, they tend to keep the outcomes. In vocalic verification outcomes across quantization levels, we have a different scenario where some timeouts start to appear, and then we have the correct outcome as far as we increase the number of bits. Here we can check the effect of quantization in the adversarial examples. So we can't properly talk about the quality because they all look almost the same. But for 8 bits resolution, that's the first row, we can see that we have huge gaps between the grayscale. That's due to the lower bits resolution. So we can see that we have many pixels as the same grayscale. And then as far as we increase, we can see the grayscale changing more. So that's examples of adversarial examples. Then we perform a comparison using XXU. So when we compared with Marble, we found that we overcame them in all of the benchmarks in using property 1. When we compared to Nerify, Nerify overcame our approach because Nerify is multi-threaded, so it takes the advantage of all the cores of the processor that it was running inside. But then we modify in order to make a fair comparison. We modified Nerify to a single thread version, so we overcame then being better in 24 of 45 benchmarks. So we were slightly better. The conclusion that we can mention here is that many of the software verification techniques that we mentioned and we used could improve the ANN verification. Our approach was significantly faster than state-of-the-art tools. Verify is faster since it deploys a multi-threaded algorithm, so it can be also a future work for our approach in order to perform better, implement a multi-threaded version. Neither Marble nor Nerify can verify quantized neural networks. It seems that our approach was the only one able to verify quantized neural networks. And do you have any questions?